So you guys having IE book?
Yes, sir. So you asked us to do 3.132 and 3.133.
Yeah. Yeah, three. Yes, correct. 3 point. 132, right?
Yes, sir.
So that was given as a homework, right? So let me draw the circuit first. So question is, what amount of heat will be generated in the circuit shown in the figure 3.30 after the switch SW is shifted from position 1 to position 2? Okay, so what you are supposed to do? So when you shift the switch to position 2, there will be some redistribution and you can say reconfiguration of charge. So the charge before and charge after will reconfigure itself. So what you're supposed to do is you're supposed to draw two circuit. One when the position is 1, when the switch is here, and if the switch is here, the circuit will look like this. So in the past scenario, when the switch is at position 1, we can find the charge distribution using the or by reducing the circuit. So we know that the total charge leaving the cell will be C equivalent into E, correct? And why we are using this formula? Because here the circuit is reducible. You can check. But when you make the switch, this will look like this. And fortunately, the C equivalent will be again the same. The charge here will be also C equivalent into E. But both will give you the same answer, fortunately. So this is the point. But still we need to distribute the charge first to see how charge is present on every plate. So what is the C equivalent, guys? What is C equivalent here? You can use the series parallel combination to get the C equivalent first. So everyone tell me the series, C equivalent first. Use the series parallel combination formula. You will get the answer. Tell me, guys, what is C equivalent here?
Sir, 3C by 2.
It is C, C naught, and C. It is not C, C, C.
Oh, sir.
So
Yeah.
2C C naught plus C square whole divided by C plus C naught.
So I can see it is C plus C naught into C upon 2C plus C naught.
Yes.
Do you all see the same? These two are in parallel and this is in series.
Yeah.
So parallel means C plus C naught and series means that into C upon the net value. So the answer is C plus C naught into C upon 2C plus C naught. In fact, C equality in this case is also going to be same. Do you see that?
Yes, sir.
Yes.
Because these two are in parallel and this is in series. So you get the same answer. So luckily, or you can say fortunately, the C equivalent turns out to be same. Therefore, the charge leaving the cell will be same. And that's why I have written Q only, which is C equivalent into E. In the first scenario, this charge will deposit over this plate completely. Yes or no? Tell me, guys. So can we write Q here? Because the same Q will come here and will deposit here.
Yeah.
Yes.
But when the same charge will proceed further, it will divide in two parts. And therefore, some charge will come here. And some charge will come here. Be very careful with the polarity of plus and minus charge. So you can see the distribution and if I call this as Q1, if I call this as Q2, we can use the charge divider rule to get Q1 and Q2, if you remember. So the capital Q is getting divided into two parts, Q1 and Q2, parallelly. Yes or no?
Yeah.
So as per the charge divider rule, this is proportional to C value. So this is C not Y.
C plus
And therefore Q2 will be how much?
C by C plus C not Q.
So we have all the distribution. Let's look at the distribution in the second scenario. In the second case, the Q will come here and it will divide parallelly to the C and C naught. So the C will get Q2, if you remember. And C naught will get how much? Q1, isn't it? And both charges will meet again here, Q, and this will get complete Q. So do you realize the charge distribution?
Yes, sir.
Yes or no?
Yeah.
Now you have to look carefully that going from the position 1 to position 2, although the net charge has not changed, but the charge has reconfigured itself. It means charge must have flown in the circuit to attain the new configuration, which means there must be some current, which means there must be some heat dissipation. Do you realize this?
Yeah.
Now the question is, to find the work done by the cell, we need to know what is the charge given by the cell to get the new configuration, assuming the old configuration is already present. So if you look carefully, the new configuration, how to understand the new configuration, it's a difficult task. Look at the cell in the new situation, the new position. Look at the cell, everyone. In the second scenario, the positive plate of the cell is connected to now two plates. How many of you realize this? This positive terminal is connected to these two plates. Do you realize this?
Yeah.
Yes, sir.
Yes, sir.
And you can easily calculate the net charge on these two plates in the previous situation. So in the previous situation, what is the net charge on these two plates? Tell me. So if you look at those two plates in the beginning, very beginning, what is the net charge? Capital Q minus Q1. Yes or no?
Yeah.
Do you realize this? The net charge on the two plates, which is going to connect with the cell in the next scenario, in the next case, the total charge on these two plates turns out to be Q minus Q1, right?
Yes.
But what is the new charge in the second case? On the same, those two plates.
Q1 plus Q2.
That is capital Q.
Yeah.
So the total charge now is capital Q, and earlier it was,
Q minus Q1.
which is
Q
Q2,
minus Q1.
which is Q2, right?
Yeah.
So if I write Final minus initial. Final is Q1 plus Q2, as you can see clearly. So we always check the new configuration and we compare the same plate with the old configuration. So in the old configuration, the net charge was and basically this is Q minus Q plus Q1. So to get this new configuration, how much charge the cell must have supplied? So going from this configuration to this configuration, how much charge the cell needs to supply?
Q1.
K1. And once we know the charge supplied by the cell, to attain the new configuration with respect to the previous configuration is called charge supplied. And therefore, work done by the cell is defined as E delta. Do you remember this? Do you remember this? Yes or no? Is this clear, guys? Hello, hello, hello.
Yes.
So work done by the cell is how much? EQ1, right?
Yeah.
So we can substitute the Q1 value later on, but now this is the work done by cell. To find the heat dissipation, we have to use the work energy theorem. So what is work energy theorem? So work done by the cell is delta H plus delta UC, and this we write for the system. This we write for is this clear?
Yeah.
Yes, sir.
Now, can you substitute the value of each term to get delta H? Also remember, while writing the delta UC, we calculate potential energy of all capacitor in the circuit. So tell me the answer now. What is delta UC here? So the total energy of the entire circuit will be how much? So for any reducible circuit, what we can say, the energy will be half C equivalent into V square, right? If you look at the entire circuit, the net potential across this is how much? E only. So you can write the energy directly as half C equivalent into E square. Is this clear, guys?
Yes.
Yeah.
So, so what is the initial value? I think initial is same as final. Because in both cases, the C equivalent is same. Isn't it?
Yeah.
And therefore, delta you see turns out to be 0. Luckily. So we can write delta H is actually work done by cell, which is E Q1. That's it. That is the answer. And what is Q1, by the way? So what is Q1? C not Q by?
C naught plus.
Okay. But what is, by the way, what is Q itself? What is Q? Q is
C
C
divided by V.
C plus C.
so the answer turns out to be how much? C not E square. It is clear?
Yes, sir.
So how many of you have understood this part? Everyone?
Yes.
Yes, sir.
So again, solve the same question without looking at the answer. Solve it.
Hello.
Yes.
Sir, I wanted to ask one thing.
Hmm.
You had told to join test series, so I joined that. But like majorly, many questions are from optics and thermodynamics. So how to do that now?
Optics you can watch. I mean, ray optics
And
lectures are already
modern
there.
physics.
Yeah, modern physics will be taken care later on after the EMI chapter
Okay.
is over. EMI
And
is.
wave optics also many questions were there.
Yeah, yeah. So they have taken the part which is not covered here,
Okay.
but will be covered later on. Okay.
Okay.
So you can do on your own if you can read and you can do. Yes, you can leave as of now. Not in a big issue.
Okay.
So try to solve those questions which is covered so far, and check whether you are able to do those questions or not. Okay. This question is done. Everyone, tell me.
Sir, one.
Everyone, give your honest try and get this question done.
Done.
Got the answer?
Yes.
So do the next question, the 1.333, I think. No?
Yeah.
Yeah, solve this. So those who are able to get the answer, please solve the next part, which is 1.332. The method remains same, and you have to get the answer anyhow, because if you're not able to get the answer, it means this entire concept is not clear how to proceed. So whatever time it takes, do give the time, but make sure you get the answer. Anyone getting the answer?
No, sir.
So it means you're not getting the concept right, huh?
No, sir. I'm trying the second time.
Yeah, so you have to do the same thing. You have to assume one of the cell as bigger one, others is small one. Then show the charge on each plate as per the cell value, and check the configuration before and after, and find the delta Q, write the work done by the cell, and then write the delta UC and use the work in theorem to get the delta H. This is what you're supposed to do. So we have
Yes.
finite number of steps to get the answer. Okay. So try once again. Until you're not getting the answer, it means this entire concept is not clear. So first step must be you have to show the configuration of charge when the switch is at position 1. Can you show it, everyone? And now to show the configuration of charge, you have to assume one of them either E1 or E2 as the dominant. So you can assume, let's say, either E2 is more than E1, or you can assume E1 is more than E2, such that you can show the charge polarity on the plate of capacitor. So you all guys can solve with the assumption. Assume it. So with this assumption, can you find the charge configuration in the beginning? And then show the new configuration when you change the position. And once you do so, you will be able to see the change of configuration, and hence delta Q can be calculated. Okay. So tell me, guys, or you can, okay, you can choose whatever you want. E1 is this. Okay. So at position 1, which plate will get positive charge, which will get negative charge? So at position 1, this is E1, this is E2. Can you find the charge? Since I have taken E2 is more than E1, so what is the net EMF of this combination? The net will be how much, guys? Tell me. Am audible? Hello, hello, 1 2 3, 1 2 3. Am audible, guys?
Yes, sir.
So tell me, at position 1, what is the charge on the plate of capacitor?
C into E2 minus E1.
Very good. So the initial charge on the plate of capacitor will be C E2 minus E1. And which plate will get the left or the right? Positive. So positive plate will be which plate? Left plate or right plate? Tell me. Which plate will get the positive charge? Tell me, guys. The left or the right?
Left.
Left, because E2 is more, right?
E2 is more. Yeah.
Now at position 2, what will happen? Only this will form the closed path, the other will be out of the circuit, isn't it?
Yeah.
Yes.
So now which plate will be positive charge? Right or left?
Right.
Right.
Right
Right.
one.
So with respect to the new cell, the plate is having how much charge? The plus plate, you can see, is connected to this one. So we need to check the charge on this plate in the old configuration. And if you see, what you'll get is minus C E2 minus E1. Do you get it?
Yeah.
So what is the charge on this plate right now? So how much charge is here? I think you all have forgotten the capacitor chapter 1.
E1.
CE1, right?
Yeah.
So earlier the plate was having this much charge, now it is plus CE1. So how much charge must have flown to achieve this new configuration from the old configuration? Tell me, guys. So delta Q is how much?
CE2.
C
C E2. Very good. That is the right answer, C2. And what about the UC initial? And what about the UC final? The energy stored in the system finally is how much?
half CE1 square.
And in the very beginning, how much it was?
Half CE2 minus E1.
E2 minus
Very good. So can you calculate the delta UC? How much it is coming? Tell me, guys. No, just a minute. Got the answer for delta UC?
Yes, sir.
Yes, got
How,
minus.
how much?
C E1 E2 minus half C E2 square.
Yes.
Is it like this?
Yeah.
Yes.
Okay.
E2 square.
E2 square.
Yeah.
And then delta H is how much then?
I got the answer as half C E2 square. Final answer.
Yeah, okay, that's correct answer.
Yes.
Yeah.
I found work done by sellers.
Okay, great.
Yeah.
That is C E1 E2, right?
Yes.
Yes.
Yeah, very good. So this is the right answer. And these are the two difficult questions from Eroda which you need to solve from the RC circuit and heat. So in I think 2018 or 19, JEE asked a really good question from the heat dissipation part in RC circuit. Okay. Just a minute. Okay, sorry guys, got some unwanted guest. So we are done with the RC circuit, and the next concept in this chapter, which is the last concept, is called electrical instrument. Now, electrical instrument is purely practical concept. So to solve the question of electrical instrument, or simply to solve numerical based on instrument, you need to know a lot about instruments, how they work, what is the commercial application, how it is manufactured by the manufacturer, and what are the things which we need to take care of while solving these questions. So we are moving towards the last concept from current and electricity called electrical instrument. So we are going to talk about the analog instrument. Not presently we have everything in the digital format, but when we learn for the JEE, we only talk about the analog instrument. Now, if you have seen any analog instrument, you must have seen the calibration with a needle, and the needle will
Yes.
generally oscillate over a plate with some number written over it. Okay. So oscillation of needle demands or requires some oscillating mechanism. Okay. And in most of the electrical circuit, the input parameter, or you can say the input itself, is current. So while designing electrical instrument, we try to utilize a concept called magnetic effect of current. Because whenever current flows through a loop, or you can say a conducting loop, and if that loop is kept in a strong magnetic field, it will experience torque, which will deflect the loop. And if we create some sort of mechanism in which the loop is connected with the needle, as the loop will turn, so the needle, we try to cover or hide everything in detail, and what we left to see to the user is only the needle part. So what you see is the only movement of needle, rest of the thing we don't see. Okay. So the device which is the, you can say, soul of every analog electrical instrument is called galvanometer. So first of all, we are going to learn a bit about moving coil galvanometer. So we call MCG. Okay, moving coil galvanometer. And it is a, you can say, soul of every analog device. So we need to know the physical principle on which it is based, because you may be asked to answer this question that on which physical phenomena this device operates or works or is based on. So we say that it is a device which is based on the magnetic effect of current. So the basis on which it is designed is called the magnetic effect of current, and this will be taken care in detail in a chapter called magnetism, which is your next chapter. But right now, you just need to know that there is a device called moving coil galvanometer, and it is a device which is based on the magnetic effect of current. How it looks like, you all can search and you can see, but let me draw the simplistic top view of moving coil galvanometer. So to design the moving coil galvanometer, so this is the top view which you are looking right now. So we take two bar magnet, you can say cylindrical bar magnet, in which the middle portion is cylindrical. You can see this is the empty space, and we have north pole and we have a south pole. Now between this magnet, between the pole of the magnet, we insert this joint. Okay. The next thing which we insert between the pole is called armature. Armature is basically made of an iron core. Okay. So we insert an iron core. Again, what you're looking is the top view. So it's a cylindrical iron. Okay. So in reality, it is something like this. So it is the iron core. At the center of the iron core, we have a clamp with a groove. Okay. So what you will see here, a clamp with a groove, and in the groove, we wrap a large number of turns of copper wire. Okay. So basically, it's a groove like this. You clamp over the armature or this iron core, and then you take a thin wire of copper and you wrap it. Just wrap around it. So the clamp will make sure that it will not slip or on the right or left. It will remain intact within this groove. Okay. So if I wish to draw it here, so I'll draw something like this. So as you know from the electrostatic that a medium will have something like permittivity, and in case of electrostatics, permittivity is kind of discourages the lines of force to go through it. So it will decrease the lines of force, but similarly, just a moment. Okay. Now, why we use the iron core? What is the purpose behind using the iron core? So just like electrostatics, we have something called permeability instead of permittivity. And permeability actually refers to the ability of the medium to allow the lines of force to pass through it. And iron being a ferromagnetic substance having highest permeability, and therefore it will make sure that all lines of force is passing through the core itself. And because the loop is wrapped around the core, so the lines of force will also pass through the loop, and therefore we will have something called magnetic flux. So the way we can represent this, so from North Pole, the lines of force will be radial to this iron core. And it will terminate on the South Pole. So we only consider those lines of force which is normal to the, you can say, loop. And because of the cylindrical shape, we will always have some lines of force which is perpendicular to the loop. So this iron core will be attached to a spindle. So a spindle is basically a slightly thicker rod, slightly, not much, and it is attached somewhere here. So in a way, this entire iron core is mounted on this spindle, and the spindle is kind of fixed at the bottom. So if you look at the bottom, the spindle is fixed in a container, and the top of the spindle is attached to a needle, a pointer, and this is what you see exactly. So this is, let's say, written 0, then you have some value written on the right, some value written on the left. And then minus, we can write 1, 2. And then we have a stopper. So what you see is this calibrated scale on which this pointer, and pointer basically moves because of the twist of the loop. So it is mounted, and as the loop will turn, the cylinder will turn, and so there is a twist in the spindle, and the twisted spindle will let you see the turning of needle. So generally we represent something like this. So whenever there is a current, now also you need to understand here that 0 is put at the center, in the middle, and 0 is put in the middle in devices where deflection can occur in both directions. So if the needle can deflect clockwise or anti-clockwise, so in such scenario we keep the 0 in the middle, And the two direction also gives you the two different sense of flow of current. So if clockwise current is creating the right deflection, then anti-clockwise will create the left deflection. So sometimes if you connect the battery with opposite polarity, the deflection will occur, but on the other side. So this is how we create this device. And because the current will try to create a torque. So the torque which is developed due to the current in the coil is called deflecting torque. And the deflecting torque, or you can say magnetic torque, depends on certain quantity, which you need to just remember. It is number of turns of the coil, the current which flows, the area of the loop. Here we are taking the rectangular shape of the loop, and the strength of the magnetic field in the direction normal to the loop. So this is what we take as a magnetic torque. The proof will be given in the chapter of magnetism. As of now, you just remember the formula. This is called deflecting torque. So this will deflect the needle. But from elasticity, there is something called torsional torque. So as the rod will twist, it will try to restore or try to go back to the same undeformed state. So when you twist the rod will develop something called torsional torque. And this torsional torque will be proportional to the twist which it will develop. And we put the C as a constant, you can write this as torsional torque, C theta. So we have torsional torque, which is equal to c theta, and c is called the torsional constant. Okay. Now, how we read the reading of the device? So when you send the current through the device called galvanometer, the needle will deflect. So if the deflection will occur, the rod will twist, the spindle will twist. And as a result of twist, it will try to restore or will create some restoring torque. The moment both the torque will balance out each other, the needle will attain the equilibrium. And it is the equilibrium position which you actually read on the scale, or you can say the calibrated scale. So the calibration is done in proportion to the current. Okay. So what we actually measure is the deflection, the angle theta, and what we interpret is the current. It means the angle theta and current must have some linear relationship. So at equilibrium, the NIAB is equal to c theta, and therefore theta we can write as, you can see NAB upon c into I. And you can see that as current will increase, the deflection will increase, and therefore we can calibrate the scale in proportion to the current. So what we actually measure is called angle, but what we interpret is called the current. And this is the relationship. So this theta upon I is called current sensitivity. And the current sensitivity is called output upon input. So what is output here? The deflection is the output. What is input here? The current is the input. So you're sending the current in the device, and as a result, what you're seeing the turning of the needle or rotation of the needle, or you can say deflection. So the sensitivity is simply the output upon input. So if you send a small current and if you get a bigger deflection, you can say the device is highly sensitive, isn't it? So if a small input can create a bigger output, we can say device is highly sensitive. And if the big input is creating a very small output, we can say device is very less sensitive. Is this clear, guys? What is sensitivity?
Yes.
So you need to know sensitivity, and the formula of sensitivity you can clearly see is NAB upon C. Okay. And this NAB upon C will tell you that in how many ways we can affect the sensitivity of a device. So if you increase the number of turns, you can definitely affect the sensitivity. Now the problem is, if you try to increase the number of turns, indirectly also you affect the resistance of the device, the internal resistance of the device, because more the wire you will use, more resistance it will entail accordingly. So we must trade off between things. So we need certain amount of sensitivity. A very high sensitivity is also not required. So a very high number of N is also not required. If you try to increase A, again, you need to create a bigger size device. The cost will be the issue. And if you try to increase the B, you need to use some expensive magnet, which will again incur some cost. So because we are manufacturing device for the commercial purpose, so we want to keep things commercially viable. Okay, not just for the meant for the lab. So we need sensitivity up to certain value. Maybe we are interested in measuring the microampere current, but measuring the nanoampere or picoampere is not required, because that current is of no practical use. So we decide what kind of sensitivity we are happy with. So it is all about the practical usage. Okay. No, we do also have something called voltage sensitivity. Okay. So the voltage sensitivity, we know that if we have a circuit with resistance I, resistance R, and a potential difference V, and if this circuit is attached to this device called galvanometer, so the galvanometer will have this as circuit symbol. I'll just show it again. In such case, the current, the input to the device will be V by R. The current will be V by R, and therefore the voltage sensitivity is called deflection per unit applied voltage. So deflection in the galvanometer for the per unit applied voltage is called voltage sensitivity, because here the input is voltage and output is deflection. And V we can write as I into R. Therefore, it is very interesting to know or understand that the voltage sensitivity turns out to be current sensitivity upon R. Many students, what they do, they use the formula V equals to IR, and therefore they also use the formula similar to V equals to IR for the sensitivity, but it is other way around. You can see the voltage sensitivity is current sensitivity upon R. It is not into R. Okay. So this is what you also need to remember, something called voltage sensitivity. Now this device which we have created here called the moving coil galvanometer, when it comes to the circuit, or you can say circuit notation or circuit representation, so we do simply, we write G as the name of the device, and every device will have some internal resistance, and this internal resistance is called RG, and RG is called internal resistance of galvanometer. Okay. Okay. So every device, every galvanometer will have some RG. You cannot avoid the RG. It will have some value. Although very small, technically it remains in less than 10 ohm. It may be 1 ohm, it may be 0.5 ohm, it may be 0.1 ohm as well. So this entire term, this entire representation is called a representation of galvanometer, and this A and B is called terminal of the device. Okay. So RG is the internal resistance, which is what you need to remember. And for every device, the RG value remains constant. So for one device, RG cannot change. So this is what you need to just remember. Rest is simple. Let me talk about the galvanometer, its properties. So galvanometer is highly sensitive device, and it can measure as small as macroampere range of current up to milliampere range of current. Now the problem is, although it's highly sensitive and highly accurate, it can measure a very small value. But the thing is, it can only measure a very small value. Okay. So it is able to measure only a small value. Understood? In practical life, we need current of ampere range. We need 1 ampere, 2 ampere, 10 ampere, 5 ampere, 15 ampere. So microampere or milliampere is of no use. And that is why this is called short range device. So it is a short range device. Okay. So how to make it practical? So every galvanometer will allow certain amount of current, and beyond that it will get damaged, or it will simply burn out. So if this is a device, and if there is a current, so there is a limit up to which the current can be measured with from the device without getting damaged. So the limit of a galvanometer we call IG. So IG is called current at full scale deflection of galvanometer. So you cannot measure more than IG. It is the upper limit that you can measure. Okay. Now anything less than this value is okay, but more than this will damage the. So current value, we can say if current value through the galvanometer exceeds IG, then it will damage it. So we have to take care of the damaging also. So we should not send current more than this so that it gets damaged. So on every device, we have something called tolerance limit. So if there is a fluctuation of current beyond this IG, they mention how much it can tolerate beyond the rating value, beyond the specification value. So to make a device practical, to increase the range of operation, we use another resistance, and that resistance we connect with the original galvanometer either in series or parallel, and the whole purpose is to make that device practical with in general high range of operation. So the resistance which does the altering of the range of operation of actual galvanometer, we call it shunt resistance. So we need to know something called shunt resistance. And shunt resistance is purely specification, you can say, based. So depending on what kind of a range of operation we want to achieve, we calculate the value of shunt resistance. So shunt resistance, which we represent as RS, is you can say user specification based. So every manufacturer, whoever manufactures the device, they get some sort of specification that they need to manufacture for certain range of operation, and based on the range, they think of, okay. So you can define here, it is the resistor or it is the resistance. Which is either connected in series or parallel with galvanometer in order to increase. You may decrease, but our intention is to increase its range of operation. So we want to achieve some range of operation. So the first device of practical usage that we would like to learn here is called ammeter. Now, whether it's the ammeter, voltmeter, or ohm meter, there are three devices which are very famous. The soul of every device is the MCG, moving coil galvanometer. The reason is the deflection mechanism we need. Okay, we need some sort of deflection mechanism, and that deflection mechanism can be achieved using the moving coil galvanometer. So if someone will ask you what is ammeter, what you can say? It is a device, it is a current, measuring device, and it is always connected. How we connect? In series or parallel? In a circuit. So in circuit, you connect ammeter in series or in parallel?
Series.
In series. So it is a current measuring device, and it is always connected in series in the branch through which current measurement is desired. Okay. So it is a current measuring device, and it is always connected in series in branch through which current measurement is desired. So if you wish to measure the current in a circuit through a particular branch, so let's say if you want to find the current through this branch, let's call AB, and if you have an ammeter as a device, so what you do is you cut the branch, and then you take one terminal on this side and then other on this side, and now the same current which was going from A to B, now the same current will go from A to this device, then to B, right? And we always want to let the same current to flow through the device so that we can measure it all. So our requirement is to measure the current, so it should pass through the device, and therefore it is connected in series. Now the question is how we manufacture ammeter using galvanometer. So to understand the manufacturing, you need to know some practical aspect. So you need to know some practical aspect. And what is the practical aspect? So you need to know as a manufacturer that what range of operation you would like to design your device. Okay. So the range of operation will be given to the manufacturer as something called a specification. So we would like to measure current in the range 0 to I naught ampere. So it may be, they may give you 0 to 10 ampere or 0 to 15 ampere. So generally in the household, we need current up to 15 ampere. For arc building, the current goes up to 200 ampere. But that is not for the household usage. Definitely that is for the commercial usage. So in our household, we have switchboard, we have socket. And if you have seen a socket, it is written, they mention the specification on the socket. What they mention? That this socket is a 10 ampere socket or 15 ampere socket, which means if you connect a device which will withdraw more than 15 ampere, the socket will not be able to withstand that heat and it will get damaged. It will melt, it will catch fire and so on. So every socket which is being sold comes with a ampere rating. We call it ampere rating. And when you go and buy those socket, you can read actually. Next time when you buy, you can see the box and you can read also. Now this, let's say some random manufacturer has got a kind of a specification that can you build a meter which can measure from 0 to I0 ampere. So the upper limit which we would like to measure is of importance, because if our device is ready to measure I0, then any value less than I0 will be measured without getting damaged. So the device will not get damaged and it will give you the correct reading. So I0 is called the new range. Okay. So here I0, we can simply say I also. So here I0 is called new range. Okay. So this is the new range you would like to measure. Let me keep it I itself, or I0 is also fine. Okay, I'll keep it I0. So I0 is called the new range. This is the new range up to which you would like to make the measurement. Earlier, the old range was how much? Can you guess the old range? What was the old range that we were able to measure so far using the galvanometer itself?
0 to IG.
So old range was IG.
Huh.
Very good.
Yeah.
So IG is called the old range of device. It means without modification, what it is capable of measuring without getting damaged, that is called IG. Okay. And I0 is the new range of measurement which you are interested in. And for that, you are going to create a device called emitter. So how to create this emitter? So it's very simple. Imagine we have a galvanometer. And now the diagram which I'm going to draw, that is the crucial step in solving question of emitter, voltmeter, and galvanometer. So if you're not able to draw this part of circuit, probably you won't be able to solve the question at all. So this is your galvanometer. Okay. This is your galvanometer and I0 is coming. Oh my God, it's dangerous. If this I0 will pass through the device, it will get damaged for sure. Yes or no?
Yes.
So what you want? You want only IG should go from here? Yes or no?
Yes.
Yeah.
Right? So corresponding to I0, the current that should go from the device is IG, because I0 is the maximum value and IG is the corresponding maximum value. So remaining current must deviate from this path. Yes or no? And to create the alternative path for the remaining current to go, you will create a parallel connection of resistance with the device. Yes or no?
Yes.
And this parallel connection must have the value called RS. This is called the shunt resistance. So what you are doing to create an emitter, you're creating the emitter by connecting the shunt resistance, in parallel with the galvanometer. Yes or no?
Yes.
And
Yes.
parallel is the requirement, parallel is the demand. Yes or no?
Yes.
Yes.
Now I naught is really big value. Ig is very small value in milliampere, or you can say microampere. So you tell me that to allow maximum current to pass through the alternating path must have very high resistance
Ve-
or very low resistance.
Low resistance.
Low resistance, very
resistance.
low.
Low, lesser than
RG.
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 Yeah.
So we need, because we want most of the current, because Ig is in milliampere, I naught is in ampere. So we want only 1000 part to go through the Rg, remaining to go through the Rs. So the Rs should be equally small, isn't it?
Yeah.
So this circuit is called emitter as a whole. So now what will happen? The remaining current I naught minus Ig will go through the shunt, and to allow the maximum current to pass through the shunt that we must use must be very small. Now, as a manufacturer, we have given Rg, or you can say Rg is known to us, Ig is known to us, I naught is the requirement, which is again known to us. So what we decide as a manufacturer is Rs. So that's very interesting. Here the variable is
RS.
Rs. Here we would like to know Rs value, because everything is known, because the specification will be given to you. Understood? So as a manufacturer, we decide what Rs will achieve the given range of operation. Is this clear, guys? Tell me.
Yes.
So you can see
Yeah.
emitter as a whole, this as a whole is called emitter, which we represent like this. Is this clear? Is this clear, guys? Tell me.
Yeah.
So emitter as a whole, this entire device we call emitter, but inside you can see there are two resistors in parallel. So emitter as a whole, sorry, emitter as a whole, we connect in series, but the shunt we connect in parallel. That's very interesting. How we connect emitter in circuit? Answer is series
Series.
combination. How we connect shunt in emitter? The answer is in parallel with galvanometer. Is this clear?
Yeah.
Yes.
If this circuit is in your brain, in your mind while solving question, then probably you will get the answer with ease. So given everything, these two are in parallel combination. So the potential across Rg or across Rs must be same, yes or no? Because the point, let's say A and B are same for both.
Yes.
So can we say potential Ig-Rg is the potential difference across A and B from the top, and I minus Ig, or you can say I naught minus Ig into Rs from bottom, and
Yes.
both must be same, yes or no? Tell me.
Yes.
So Ig is known to us because from the experiment, from some other, it's given to you, let's say. So what shunt will achieve this task is Ig-Rg. So that is why once you know your specification or requirement, it is very easy to decide the value of shunt that we must employ to achieve the alteration of range of operation. Is this clear, guys? Tell me. This is very important and very crucial.
Yes.
Yes, sir.
So
Yes.
this we can rewrite as Rg upon. These are multiple ways of writing. Then I naught upon Ig minus 1. And I naught upon Ig is actually new range upon old range, right?
Yeah.
And this is called n factor. So let's say even nothing is given. Let's say if you want to enhance the range of operation 10 times, 20 times. So what is given to you directly? I naught by Ig.
In fact, yes.
N factor is given to you. Because many times in examination, you need to express your answer of shunt resistance in terms of n factor, and the answer is n minus 1. So if you want to increase the n factor 1000 times, the shunt must be Rg upon 999. Is this clear?
Yes.
So if you want to achieve 1,000 times, improvement, let's say if you want to go from milliampere to emitter, 1 ampere. So 1 milliampere is very small quantity. 1 ampere is much bigger than 1 milliampere. How many times?
1000.
1000 times.
So the shunt should be Rg upon.
999.
999.
Yeah. So let's say if I tell you, okay, that the resistance of the galvanometer is 0.99 ohm. Okay. And N factor is 1000. So what is the value of shunt resistance? So 0.99 ohm upon 999, correct?
Yes.
Yeah.
That is equals to how much? I don't know. -3, right? 10 power -3. 1 milli ohm. Correct? I think that is the answer. Right? It is clear.
Yeah.
Okay. So I hope this is clear.
Yes.
Yes.
Any doubt? So quickly we'll go for the next device called voltmeter. Now, if you want to solve the circuit of ammeter voltmeter, problem of ammeter voltmeter, the first step is simply draw this circuit and you're done. If you're able to draw the circuit, if you're able to write these values, I not IG, RS, RG, if you can write this entire term on your own, you can easily solve the question. So the next device is called voltmeter. So what is voltmeter, guys? What it measures? Tell me. So it is a device used to measure the
Volt.
potential difference or voltage, right?
Yes.
When we talk about the potential difference of voltage, we measure across some branch. Okay, potential across a branch. Or circuit element. Okay. And how we connect? Tell me, guys, how we connect?
Parallel.
Parallel.
Yeah, in parallel to the branch, right?
Yes.
Yes.
Okay. So now if you go back to the old circuit, and that is why it's difficult. So if you go back to the original galvanometer, this was your device, right? What is the maximum current it can tolerate? Your original device can tolerate how much
IG.
current?
IG.
So across its terminal, what is the maximum potential difference we can achieve?
IGRG.
IGR.
So this is called VG, the old range. So what is VG here? IGRG. Now it looks really simple, but again, you need to know that you have to write this. IGRG equals to VG. So what is VG called here? Old range, because we cannot measure more than this, because if we increase the current more than IG, it will get damaged. So we cannot go beyond IG, right? So what
Yes.
way is left? What way is left to get more value? How we can achieve the bigger range of operation? Can we increase the IG?
No.
No.
So what we are left with the option? Which option we are left with?
Decrease or
Decrease.
increase or increase. Sir.
Correct. So what we do is we connect a register in series, and again this will be none other than the new shunt resistance. And mind it, this shunt is not the same as the old shunt which we got for the ammeter. Shunt is context based, right? So here the requirement is different. And because you want to increase the range of operation, the shunt should be bigger or smaller. What do you think? The shunt now that we are going to use should be bigger or smaller? Tell me.
Bigger.
Bigger.
Not just bigger, much bigger, because we want to operate under certain conditions, maybe 1,000 times more. So let's say you get a specification that can you design a device called voltmeter which can measure from 0 to V0. This is the specification given to manufacturer. So what manufacturer will do? He will make sure that the new device can reach up to V0. Yes or no? So you will increase the shunt as per the requirement. Yes or no?
Yeah.
Isn't it? Because our job is just to reach V0 value. Because the specification says that design your new device called voltmeter, which can measure up to potential V0, which may be 30 volt, 20 volt, 50 volt. Okay. So now V0 we can write as how much? What is V0, guys? Tell me. Come on, tell me. What is V0?
IG times RG
IG
plus
RG plus R.
RS.
RS.
Now here V0 is given to you because that is the specification. IG is a constant value for a device because we cannot alter the IG. So here the RS is something new. RS is for the shunt resistance, and that is what we are trying to determine here, right? So you know the two formula, equation 1 and 2. IG is going to be same. So how to get RS using equation 1 and 2? Which quantity is not required here? What is not required here? See, this is the new range. We need to know the new range. We need to know the old range, right?
Yeah.
What we don't need to know here?
RG.
IG, because IG is the old range for current. So in voltage calculation, we don't need IG. So to get rid of IG, what we can do? We can divide.
Yeah.
That's easy way, right?
Hmm.
And that is why this voltmeter is difficult to solve, because this will not click in the examination until you are not learning here carefully. So if you divide 2 by 1, what you can write? V0 by Vg equals to, and we are done. This is 1 plus
RS by
RS
RG.
by Rg. And this V0 by Vg is called what? N factor.
In fact,
I have discussed about it. So N is 1 plus RS by Rg. This implies what is shunt value, guys? N minus 1 into.
RG.
So if you want to increase the range of operation by 1,000 times, the shunt must have the value. How much? 999 times Rg.
Yes.
Is this clear?
Yes.
Now, based on these two concepts, we have very nice question asked in JEE Advanced. So quickly, I'll give you that question so that you all can practice and solve. Okay. So let me give the question quickly. Anyone having the 41 years or 42 years, whatever,
Yes.
yes.
just open it quickly. Go to the current chapter. I will also search. I should have. Yeah, got it. So go to the current chapter.
Yes.
Are you there in current chapter?
Yes.
Yes.
I think this was a question of 2014. Hopefully. Yeah, I got it. I'm there also. So just a moment. I'm almost there in the JEE section. 2014. 27. Yes. JEE advance. If you have got, then you can share in the group.
It is a single correct question.
I think it is integer.
Okay.
Where is the integer based question? Receive, tell me, you have done this before, no?
Is there
Yes, sir. What?
Integer based question is where?
on page 123 of the
Wha-
book?
Can you share it on
Yes.
WhatsApp? Yeah, I got it. I think. What is this? Yeah, question number 4.
Yes.
Yes, solve question number 4. Everyone. What Mugdha has shared, I think. Yes. So you all got the question? You can see question number 4.
Yes, sir.
So read the question carefully. Attempt with the concept which you have understood here, and you will get the answer for sure. It's easy. Take 5 minutes or 6 minutes. That's sufficient. So anyone getting the answer? See, it is
Sir,
based on
one
this only these two concepts. You have to use this from, see, you have to draw the circuit, write the circuit equation, and then solve. And always remember, shunt depends on the context. So shunt of voltmeter is different from shunt of ammeter. But what remains same in both cases? What remains same in both cases? IG and RG, isn't it?
IG.
yes, sir.
Yes.
So this is the concept that you have to use. So can you think once
Yes.
again? If you have understood, you can think once again. Okay.
Sir, I got.
You got the answer?
Yeah.
Very good. Yeah, Archit Garg. Kanu, you got the answer, Kanu? Everyone, you all should get the answer. I'm waiting for the answer. एक तो लॉक हो जाएगा।
Sir, I got the answer.
How much you got the answer?
What is the
Five.
answer?
Answer is 5. Very
Five.
good. Very good.
Yes, sir.
Yeah.
5 is the right answer.
Yes, sir, got it.
Very good. So you all got the answer, everyone?
Yeah.
Okay, so those who have not got the answer will practice at home. The next lecture will continue with the same electrical instrument with the remaining instrument. And I think next lecture will be the last lecture, hopefully. And then we'll move towards the topic called conduction. That is from the heat chapter, because conduction is similar to the current chapter. So if you know this current, you can also solve almost all question of conduction with ease. And then we'll go towards magnetism. Okay. So see you guys in the next lecture. Bye and take care.
Thank you, sir.
Bye, sir.